All right, these notes are going to start off our next unit, which is all about chemical reactions. And these notes we're going to talk about what a chemical reaction is, how we can tell a chemical reaction has taken place, and then how do we balance chemical reactions. Our first question is, what is a chemical reaction? And we've talked about chemical reactions a little bit in the past, but let's review. So a chemical reaction is a process by which the atoms of one or more substances are rearranged to form different substances. And if we look here at our example, we've got a chemical reaction here between methane, which is CH4, and oxygen, which is O2. And we can see, just even looking at the picture, that these atoms are being arranged from before versus after, right? Before we've got the carbon here in black attached to 4 different hydrogens, and each of the oxygens are attached to each other. Well, in the end, we have a rearrangement here. We have this carbon now attached to the 2 oxygens, and 2 other oxygens attached to those hydrogens. So we have this rearrangement of atoms to make new different substances. And so our products are CO2 and H2O. So this is what we would call a chemical reaction. Our second question is, how can we tell when a chemical reaction has even taken place? So here are some evidences that we can look for when we mix things together to see if a chemical reaction has actually taken place. So there are 5 things here that we can look for. We can look for a temperature change. So the temperature can either get hotter or colder, and that will be evidence for a chemical reaction. We could have a color change, like in this example right here, where we're adding red to blue, green, and it makes purple. Okay, so we've got a color change happening. And an odor can also be evidence for a chemical change, just like we saw in the smell lab that we did last semester. Or we can have gas bubbles, okay, like here. This is coming out in the gas stage. And then our last evidence for a chemical reaction would be what's something called precipitation. Okay, a precipitation does not mean rain. Okay, it basically means an appearance of a solid. So if we take a look at this last example right here, okay, we can see that there's a liquid going into another clear liquid, but as they pour together, a chemical reaction takes place, and we get this cloudy yellow stuff. That's what we call a precipitation. Okay, so that's the precipitation, this cloudy yellow stuff. So those are 5 ways that we can see that a chemical reaction has indeed occurred. All right, our third question is, how do chemists represent chemical reactions? And the way they do that is by what we call chemical equations. They show the reactants, which are the starting substances, and the products, which are the substances that are formed after, during the reaction. And they're shown in this way, if you take a look at our example here. So in this one, it shows the reactants, which are separated by a plus sign. So it's like we're adding 2 things together. And next is the arrow here, which means react to form or yield. We could use either one of those terms. So anything after that arrow is our product. So anything on the right side of the arrow is a product. And so this FeCl3 is the product actually in this chemical equation. So we have our reactants on the left side of the arrow, our arrow, which means that these guys react to form, and then everything on the right side of the arrow is our products. And we also see that we've got these little things in parentheses, right, that are going to give us the state of matter that these chemicals are in. Now, you've probably seen these before. The little S is going to mean solid, the L is going to mean liquid, G is for gas, and AQ, you'll see sometimes AQ, which means aqueous, and aqueous means that it's been dissolved in water. Okay, so that might be the only new one. Aqueous, which means that chemical has been dissolved in water. All right, so when chemists are representing chemical reactions via chemical equations, there's one thing that they must consider, okay, that chemical reactions have to reflect the law of conservation of mass, okay, which says that mass can neither be created nor destroyed during a chemical reaction. So you don't gain mass, you don't lose mass during a chemical reaction. It has to be the same before and after. If we take a look at this picture down here, this kind of illustrates that for us. Here we've got, the reactants before, okay, and they weigh, 300.23 grams. And then the reaction takes place. They shake it up. The reaction takes place. And afterwards, again, it still weighs 300.32 grams. What that means is that we haven't lost any atoms, okay, that we started with. And we didn't gain any atoms out, from nowhere. So when we're working with chemical equations, the one thing that we always have to keep in mind is that the number of atoms of each element must be equal, okay, on both sides of that reaction arrow. So we need to have the same number of atoms before and the same number of atoms after, okay? So that's where the balancing equations is going to take place. So the rest of the notes, the last question in our notes is going to be how to balance equations and a bunch of, examples of balancing equations. Our last question in these notes has to deal with the fact that we have to figure out how to get the same number of atoms on both sides of the arrow. So to do this, we have to look at the chemical equation and realize that there are two different kinds of numbers within this equation. We have the numbers out front, this 2, this 3, and this other 2 here, which are called coefficients, and they tell you the number of molecules taking place in the reaction. We also have these little ones within the molecule. These are what we call subscripts, and they're going to tell us the number of atoms in the molecule. So they're two different numbers. One tells us how many molecules in the reaction, and the other tells us how many atoms within the molecule. Now, we can only change the coefficients. Okay, so we can only change these numbers out front. Here, we cannot change the subscripts. The subscripts we must keep alone because they are there to make that molecule neutral. So let's put that down in our notes. So we're going to put that important fact in our notes that when you're balancing a chemical equation, you can only change, the coefficients, okay? Not the subscripts, not those little ones out front, okay? So let's take a look and see how we do this. What is the method for balancing these chemical equations? Before we start getting into some examples, I'm going to give you some hints as to how to balance chemical equations. So the easiest way is to take inventory of each atom on both sides of the arrow, and then you're going to play with the coefficients, meaning that you're going to change them and then kind of retake inventory and see if you can get, the same amount or equal amount of atoms on both sides of the equations. And if not, then you got to change, something else. And so it's a a give and take here. So you're going to have to, kind of play with it and experiment a little bit with these numbers. Now, once you get the numbers, you want to always simplify down to the nearest whole number. So, if all of the coefficients that you figure out can be divided by 2, then divide by 2 and simplify down to the nearest whole number. Another trick is to save the oxygen and hydrogens for last. Okay, those are usually, the hardest to do, so save them for last. And last but not least, sometimes you're going to kind of end up with this odd number that just won't balance. Like it'll end up, you have to have a half of something. We're not going to deal with halves or fractions when we're balancing equations. So to get rid of that odd number, the thing that you do is to get rid of any odd number, you double it and times it by 2, and it automatically becomes an even number. So if you're stuck with one coefficient that just it's odd and it doesn't want to balance, double all the rest of the coefficients and then you should be good. So those are some tricks that you should write down before you get to the next slide. The next slide, we're going to do a couple of examples together so that you're ready to go tomorrow in class. Our first example is here with zinc plus hydrochloric acid reacts to form zinc 2 chloride and hydrogen. All right, so the first thing we do in balancing equations is taking inventory of how many atoms of each element we have on both sides. So I like to draw an arrow down where the, or a line down where the arrow is, just to divide the reactants from the products. And the next thing we're going to do is list out all of the elements that are in this reaction. And here we've got 3. We have zinc on both sides, we have hydrogen on both sides, and we have chlorine on both sides. Now once we've listed them, we're going to take inventory. We're going to count up how many atoms of each element we have. So on the left we have 1 zinc, we have 1 H, and we have 1 Cl. And on the right we have 1 zinc, we have 2 H's because we've got this subscript here, and we have 2 Cl's because again of that subscript. All right, so we can see that it is not balanced with those H's and Cl's. All right, so now we get to play with these numbers. So what we're going to do is we're going to start with Cl because zinc is already balanced. So we're going to start with Cl, that is unbalanced. And in order for us to get it balanced, we need to have 2 chlorines on the left side to match the 2 chlorines on the right side. So again, remember we cannot add a 2 here. That is a no-no, okay? So what we do is we add a coefficient, a 2, out here, out front. So anytime we have a coefficient, it's just like in math where it's distributed or it's multiplied. So 2 out here times the 1 chlorine that we have here is going to be 2 chlorines. So we're going to cross that 1 out and put a 2. All right, so we've got 2 chlorines on that side. Now we've added that 2 out front here, and it's not changed just the chlorine. It has also changed the number of hydrogens as well. So we also have to retake inventory for the hydrogens and find that it's a 2. So now we see that the zinc is balanced, the hydrogens are balanced, and the chlorine is balanced. So that's a pretty easy one in just adding that coefficient of 2 in front of the HCl. Let's take a look at a little more difficult example. Our second example is for the combustion of propane gas to form carbon dioxide and water. So again, the first thing we do is draw a line down where the arrow is to separate the reactants from the products, and we're going to list out all of the elements that are in this reaction. So for this reaction, we have carbon, hydrogen, and oxygen on both sides. Next step is to take inventory or count up how many atoms of each element we have on both sides. So on the left we have 3 carbons, we have 8 hydrogens, and we have 2 oxygens. And on the right side we have 1 carbon, 2 hydrogens, and we have 2 plus the 1, so we have 3 oxygens on that side. Okay, so our next step after that is to say, okay, so obviously they're not balanced. None of them are balanced. So we're going to keep the H's and the O's for last. So we'll start with carbon. We have 3 carbons on the left, and we need to balance that and make 3 carbons on the right. So again, the only way we can do that is to add a 3 coefficient out here to make 3 carbons. Now, when we do that, we not only change the carbons, we also change those oxygens. So now instead of having 2 oxygens, we have 2 times 3, which is 6. So we've also changed the number of oxygens to 6. All right, so our carbons now are balanced. And so let's take a look and do the next. Okay, so hydrogen is next on our list. So let's take a look and balance that one. So we've got 8 on the left and 2 on the right. So in order to get, go from 2 to 8, we have to multiply that by 4. Right, so we're going to put a 4 out front here, and that's going to make 4 times 2 is 8 hydrogens on the right-hand side to equal the 8 hydrogens on the left-hand side. Now, again, because it's a compound, it's not just H there, it's H2O, we also change the number of oxygens. So now we have the 6 over here in carbon dioxide, plus we have 4 times 1 is 4 over here in the water. So we have 6 plus 4, which is actually 10 oxygen atoms all together on the right-hand side. So we have to take a look on the left-hand side and balance that out. So you can think to yourself, 2 times what equals 10? And for us, that would be 5. So we're going to put a 5 out here as a coefficient for the oxygen on the left-hand side. And so 5 times 2 is now 10 oxygens on the left, which matches the 10 on the right. So now we have a balanced chemical equation that follows the law of conservation of mass. All right, so tomorrow we're going to do lots of examples balancing equations.